Okay, hello students. And so in the final video for this week in our lecture here, I want to address this relationship right here. Because of all the things we discussed in the previous videos for this week, it's pretty stunning the differences in interpretation between the two quantities here, which are namely the standard deviation of the mean, this one right here, and the standard deviation. The interpretation is just stunningly different. Standard deviation is more or less constant. 68% chance your next measurement will fall between the average plus or minus one standard deviation, where all you have to do is divide by the square number of your data points, and suddenly you sort of have something that more reflects the truth, which I guess we're all after here. It says, hey, if you report your result plus or minus the standard deviation of the mean, then there's a 68% chance that the actual value you're looking for, the correct one, is within the average value plus or minus the standard deviation of the mean. So I think this is quite remarkable. So there's this thing called x bar that we're doing, plus or minus standard deviation of the mean. Then there's of course this x plus or minus the standard deviation. Okay, so this one here, I'm not quite sure what it's good for here, but this one here definitely is allowing me to see that there can be some eventual truth in the experimental work that I do. So what I like to do in this video is just show you where this comes from. And this is just one of my favorite derivations, and I don't know, maybe all of physics, because it's so simple and so neat, okay? So really what we're after then is we know that we can calculate the average of a bunch of data points, x1 plus x2 plus whatever, all the way to n number of data points, and we divide by capital N, and this gives us the average. So really what we're after then is, okay, if I calculate the average like that using the formula here, what plus or minus do I put on the average? Like, what do I put here? So we're really looking for the error in the average, and that's what the standard deviation of the mean really is, okay? And so a couple of things here that we know is that, believe it or not, this whole result can just be get using propagation of the error. Which is something that we studied last week. The whole result can just come from that. Why is that? Well, because we know that x1, the first data point we took, has an uncertainty about it. We know that x2 has an uncertainty about it, and we know that x3 and so on all have uncertainties about them, okay? And furthermore, the best estimate that we have on all these uncertainties, yeah, they might vary a little bit, would be the standard deviation. Because remember, the standard deviation is sort of the average fluctuation of any individual data point about the mean, so we sort of know some things here, okay? So really what we want to do then, as you can see, we have a formula for the average right here. There it is right there. It's the one that we've just known forever here. We know the uncertainty, so this is the first thing we know. The second thing we know is we know the uncertainty in the measurements. Let's propagate those uncertainties in the individual data points through to see what uncertainty they would eventually give in the average themselves. Okay, that's what we're going to do. Okay, so the way this starts then is if you look on basically page 75 of your book. You don't have to look there now because I'll just tell you the result. It says how to propagate error when you have a function that you want, which is a function of many variables here. So the function in this case here that we're after here is just the average function that we're working on, right? In other words, we have x1, x2, all the way down to xn, and these are all sort of the data points, and we put in to our function. So I guess our function is something like the sum of xn over capital N. That's the function. So we just like to see, if we put it through this function here, what uncertainty do we have to come out with? The last time you did this was in cratering, when you dealt with that log function. You had to send uncertainties through the log function. There was sort of a funny thing you had to do. So we're doing a similar thing here. Anyway, so that formula that we are after, that's on page 75, sort of looks like this. It says, look, if you have a function q here, which is a function of many variables, say a, b, c, and d. Just it can have all the way as many as you want. If you have a function like that, and you're trying to compute that function, and you like, which of course you can just by computing the function, but now you'd like the uncertainty in that function, the uncertainty in q. Well, that's what the formula on page 75 tells you, and it just comes from good old random errors and uncertainties. It says, okay, it's a quadrature thing once again, so there's going to be a big square root thing like this. It's going to be the derivative of function q with respect to a times the uncertainty in a, and of course squared, plus the derivative of q with respect to the next variable, b, times the uncertainty in b, and of course that whole thing's squared. And it just goes on and on and on like that. You just sort of add in quadrature these little forms here, which are none other than how the function changes with respect to a given parameter times the uncertainty in that parameter itself. How the function changes with respect to this parameter, with respect to the uncertainty in that parameter itself. And so what do we have in this experiment here? Well, our average function, so Q here is just basically going to be the average that we're trying to take here, the sum here. That's going to be our average function here, okay? That's the function that we'd like to know the uncertainty of here. And instead of all the A, B, C, D and all that business here, well, we know that Q is a function of our data points, x1, x2, x3. I guess I don't mean plus in here. I meant ... all the way down to the number of data points. Q is a function of all these things. So let's just adapt this formula to this and see what we get. So the uncertainty then, because Q is our average function here, so maybe I'll even go up here and instead of writing like this, maybe I won't even write this Q right here. Maybe I'll think of the Q as the x bar here, because the x bar really is a function of all of my data points, isn't it? So I'll just say then the uncertainty in x bar, we'll just get rid of the Q, just change the nomenclature a bit here. The uncertainty in the average then is going to be this big square root function, just the form I have above, big square root here. It'll be the derivative of the average with respect to data point x1 times the uncertainty in x1. Whole thing squared. Plus the derivative of the average function with respect to the next data point times the uncertainty in that data point. Isn't this cool the way this comes out? You just keep doing that. So you just keep doing two things. Look at how the average changes with respect to a data point and multiply by the uncertainty of that data point itself squared, and just keep adding a quadrant like that. Now the real fun part about the derivation, in my opinion, is how everything simplifies here. So it sort of looks like this. And I need another sheet here. There it is right there. Okay, so what do we get first of all? So we can recognize that any of these derivatives here, because the average function, remember, is just something like x1 plus x2 plus blah blah all the way down to xn divided by n. The derivatives are fairly easy to see. So any derivative of the average with respect to any one of the data points, xn, is just going to be equal to 1 over n. Right? Because the derivative with respect to, say the derivative of the average with respect to x1, well, dx bar dx1, this just drops around away to 1, but we have the 1 over n right there. So this is just generally something that holds for all of the derivatives. The average depends linearly on all of our data points, and we're just taking the derivative, partial derivative, I guess in this case here, of the average with respect to either one of the data points. So it's a fairly simple derivative. Next, we also know that any uncertainty in one of the individual data points is just that standard deviation. That's what the standard deviation is. It's the average spread of our data with respect to the mean, and that's our best estimate for the error on an individual data point. Yes, I know you may be writing raw ones down on a per data point interval, say where a ball drops relative to a tape measure, but the standard deviation is a pretty solid estimate of that for the data overall. And so if we plug all this into this formula here, then basically we'll get something like this here, the uncertainty in that average, which is what we're after right here. Remember, all those derivatives are just going to be 1 over n, like that. And all the uncertainties are just going to be the standard deviation. So we're going to sort of have something like looks like this in here. Plus 1 over n times sigma x squared. And it just sort of keeps going like that, and we have sort of n of these terms inside of the parentheses here. There's n of these because we have n data points. Because remember, this sum here is going to go all the way down to the nth data point right here. This term here will sort of involve the nth data point here. So again, working on the simplification a bit more, the uncertainty in the average that we're computing here is basically just going to be, since we have n of them, capital N times 1 over n squared times the standard deviation squared. That's what we'll get. So I've simplified it all down because we have n of these here. That's what this term is right here. There's n of these, and so that's what that is right there. And they all come out to be the same. If we work on that square right there, it'll be 1 over n squared, and there's the standard deviation squared. So the last line then is that the uncertainty in the average here is just going to be, all we have to do is simplify now here. We're going to have basically the standard deviation, the square root gets rid of the square, divided by the square root of n, and there it goes. And I just think that's just a great sort of simple result in there. Just a few more things to say about it. So hopefully you see the simplification here. This end cancels that right there, and you can see where the simplification comes from. And so we have it. And so the uncertainty in our average is the standard deviation of the numbers divided by the square root of n. So now we are just justified in writing result as x bar plus or minus the standard deviation divided by the square root of n. All comes from propagation of error. And so I will close this video then with a little bit of reading out of your book once again. And here it is. Comes from page 148. And it sort of goes like this. We have arrived at the desired result, which is this one right here that I just showed you here. We should pause and review its significance. We imagine a large number of experiments. In each we made n measurements, and of x we computed the average of those n measurements. So careful when he refers to the word experiments right here. It isn't like you have to go on different days of doing it. It's just when you sort of repeat your measurement over and over, like you keep dropping the ball into the sand, or you keep choosing a different wavelength for your Planck's constant, or whatever you're going to be doing like that. So it isn't like different days of the experiment, although they can be. But we have shown after repeating this experiment many, many times, our answers for x bar will be normally distributed. That's our random errors. And they will be centered around the true value x, and the width of their distribution then is our good old standard deviation of the mean. Okay? So the width of the standard deviation of the mean, notice a little x bar in here, it's not standard deviation, but of the mean now, that's our key parameter. The 68% confidence limit for our experiment. If we find the mean of n measurements once, we can be 68% confident that our answer lies within a distance of sigma, standard deviation of the mean, of the true value of x. This result is exactly what should be signified by uncertainty of the mean. It also explains clearly why the uncertainty is called the standard deviation of the mean. It's not the standard deviation, but it's of the mean of your measurements here, because it involves that x bar right there. I always have a little chuckle out of his last statements here. Say, well, with this simple and elegant proof, he does a slightly different variation versus the one I did here. All the results quoted in the chapters earlier concerning random uncertainties have now been justified. So I sort of look at this and go, wow, it's all been justified. But okay, it's just a very nice conclusion to get here. So anyway, hope you enjoy that. That's where it comes from. And so if I just recap just a bit here, it is a fairly straightforward derivation that just came from error propagation, right? We just propagated the error through and got the error in the average function. And I just hope that you appreciate then the drastic different interpretation of SDOM, standard deviation of the mean, or standard error, versus just standard deviation.